Should I start or? Ah.
So welcome to the Gemini Center seminar series. Today we have Morten Øygarden. He has a master's degree in algebraic geometry from the University of Bergen. Then he did a PhD at Simula UIB in 2021 on the topic of algebraic analysis of post-quantum cryptography. He currently is a postdoc at Simula UIB, and today he will talk about post-quantum signature schemes and the oil-and-vinegar problem. Please just go ahead and take it from here.
Yes, thank you very much. So this is going to be the third talk at the Gemini Center about post-quantum cryptography. So Carlos a while back talked about everything quantum and post-quantum cryptography. Hans talked more about lattice-based cryptography. So we're trying to do something that's a little bit different from that. So this is going to focus on another type of cryptography, the oil-and-vinegar problem, which is more about solving a system of polynomial equations. Yes, I'm not going to assume anything from one of these previous talks as well. So I'm thinking to have sort of three parts here. First, we're going to talk a little bit about what's the status of post-quantum standardization, or kind of standardization of post-quantum cryptography. Then we're going to introduce signature schemes and kind of what this oil-and-vinegar signature scheme is all about. And then at the end, we're going to talk a little bit about security analysis, what type of attacks and algorithms are kind of seeing to try and break this problem. Yes, there we go. Okay, so first of all, I'm assuming that the motivation for post-quantum cryptography is known to this audience. So essentially, we have Shor's algorithm that can break a lot of the cryptography that we're using today. So if someone were to build a large quantum computer that can actually run Shor's algorithm for these parameters in the near future, would have a very bad time. So in 2017, we started this large standardization process to find post-quantum cryptography algorithms. Those would be algorithms we believe are hard to solve, even with large quantum computers. So this is a public process where people from all around the world, academics and all that, can kind of analyze and evaluate the security of these algorithms. And there were initially 69 algorithms were submitted, and this number was sort of gradually narrowed down over 3 rounds. And eventually, last year, we kind of found 4 algorithms that we selected for standardization. So there are kind of 2 different cryptographic algorithms we're looking at. So one of them would be a KEM, that's the key encapsulation mechanism. So if you think kind of encryption, decryption, if that's a picture you have in your mind for cryptography, that would be close to that. The other ones are signature algorithms, which are more about me trying to kind of convince you that I did indeed send a certain file to you. So as you can see, there's 4 algorithms that we standardized. 3 of them are based on lattices, which was the type that Hans talked about earlier. And one of them are based on hash functions. So, I mean, that's great, right? I mean, we found some standards and everything. So what's left to do? Well, first of all, I mean, the standards are almost there. I mean, the technical documents are still kind of being commented upon, but things are very, very close. And of course, I guess arguably that's when the real job begins, because that's where you have this post-quantum migration. So people actually have to implement and kind of switch to using these algorithms. But I think from a kind of, I suppose, researcher perspective, then kind of this part of the job is done. I mean, of course, there's still going to be a lot of work on security analysis for these schemes. Lattice-based attacks are hopefully still going to be studied. But in a sense, we've kind of agreed as a community that kind of, at least these problems have reached a certain kind of maturity. I'd also say that kind of more practical settings and attacks will kind of be even more relevant now that we're going to implement stuff. So this could be things looking into secure implementation of these algorithms. We could have side channel analysis. That's kind of more in addition to not only looking at kind of the mathematics, you're also kind of looking at, is it possible to gain certain hints, right? Can you kind of gain some information about kind of timing, energy consumption, all that kind of stuff. Because kind of at the end of the day, the cryptography is being implemented on some hardware, and kind of that can potentially leak information. So that's not to say that we haven't looked at site analysis yet, but these kind of things would be kind of even more relevant now that we're going to actually implement stuff. So finally, there's kind of also a lot of interest in algorithms based on other problems. So I did mention there's a lot of lattices that we have in our standards. And it would be very good to have different problems as well that we could use. So, I mean, one argument would be the security argument. I mean, we don't really want all our eggs in one basket. So kind of if there is some sort of breakthrough to how we understand lattices, it would be great to have a different problem we kind of switch on to. There's also a performance argument to this. So lattice-based algorithms could be very, very good for certain scenarios, but maybe in other settings, we really want something with another performance characteristic. So having different problems could kind of alleviate this. And actually, we're kind of doing this for the key encapsulation things. So I said there were 3 rounds, but there are a number of key encapsulation algorithms that's gone to a bonus round, a 4th round. So I think there's 3, well, technically 4, but like most realistically 3 algorithms that's going to that we're looking at. So in the near future, we're probably going to have another chem that's based on kind of error correction codes, kind of code-based cryptography. We also want something similar for signature algorithms, but the problem is that the alternatives, kind of the ones that weren't standardized, I mean, there are no good alternatives among what we've looked at. So this is kind of bad, and the sort of solution that we sort of came up with was that, I mean, we had one standardization process, and that was pretty fun. So let's start another one, but for signatures. So that is what we're going for. And there's been a lot of new submissions going just for signatures. And this was, they were kind of released July this year. So this is still kind of very much fresh and new. So these are 40 new algorithms that are different from the ones that was submitted in 2017. And in particular, 7 of these are actually based to some extent on what's known as the oil-and-vinegar scheme, or the unbalanced oil-and-vinegar scheme, which we're going to talk about today. So I'm going to come back to the name. Hopefully that'll make sense. But yes, this is kind of where our focus will lie. So that takes us to the second part of this talk, where actually we'll be talking about what this signature scheme is and kind of how it works, what's the idea behind it. So I think this is a good place to actually start talking about what a signature scheme is. I kind of hinted at this in the introduction, but if we kind of narrow it down a little bit, and there's kind of several variants to this, but this is the variant I'm going for here. You can think of this as you have a function P that is the public key. So this is known to everyone. And it's essentially a function between vector spaces of finite fields. So we want this function to be surjective, or at least very close to being surjective. I mean, we can live with a little bit of slack here, but yeah, close to surjective. It should be very easy to evaluate for everyone knowing using this. But only one person, the legitimate user, can be able to find pre-images and sort of invert it in a sense. So essentially, for any given y, you should be able to only one user should be able to easily find an x such that p of x is equal to y. So for everyone else, this is going to be very hard. So this last property is known as kind of a trapdoor function. So essentially, if this public key is Alice's public key, then she has to sort of create P in a manner so that she knows the secret about it, but no one else can kind of find that. So let's start to look at what this P might be. So this is all just the same things, just for reference and kind of made smaller. So Now, I'm sorry. Yes, before we talk about what P is going to be, let's kind of talk about how this is being used, what the signature scheme is being used for. So we say that P is Alice's public key, and kind of everyone knows P, and everyone knows that kind of this belongs to Alice. And suppose Alice wants to convince Bob that she indeed is the sender of a document Y. And this is typically it's going to be the hash of a document or whatever you want you're going to send. So what Alice can do is to first find such an S in the pre-image of Y under P, or P inverse. And this is what we call a signature, and kind of remember that this is something that Alice could easily do. So Alice is now going to send both the signature and Y to Bob, and Bob, knowing P, can kind of verify that P of S is indeed equal to Y. And Bob also knows that kind of P belong to Alice, and Alice is the only one that can kind of find pre-images, so definitely it has to be Alice that sent this file. So that is the idea we're having. So how to actually create such a piece? Let's have a look at what's known as the MQ signatures, the multivariate signatures. And the idea here is going to be to let P be a set of M polynomials in N variables. So we typically take these to be quadratic polynomials because we don't want something linear that's kind of easy to solve. And I mean, we don't want P to be too big. So kind of if we take them to be cubic or larger, then kind of typically very big. And we want kind of the number of variables to be larger than the number of polynomials. It should also be mentioned that kind of finding such a pre-image, actually kind of solving this for X, amounts to kind of finding a solution to the polynomial system. And we know that this is an NP-complete problem in the hard case. It's also widely believed to be hard on the average case as well. It's been very well studied, and also even for kind of N and M being closed, right? So kind of we said that N wants to be, we want N to be a little bit larger than M. Right. So kind of if you're choosing these to be polynomials, let's kind of go back and see if we're kind of hitting everything we wanted. So is this close to being surjective? Well, I mean, if we choose N large enough, then we have a lot of variables and relatively few polynomials. I mean, this is reasonably surjective, kind of with a high probability, or close to, as I said. Well, it's of course very easy to evaluate. This is just polynomial, so there's no kind of hard mathematical operations there. This is sort of suggesting that it's going to be hard for everyone. So, I mean, that's a good start. But there's still kind of one piece missing, and this is kind of the trapdoor functionality. So we want Alice to be able to do this easily, but not everyone else. So this is kind of where the UOV part come in. And this is kind of how we are going to construct this polynomial system. So we start by sort of splitting the set of variables into two, X's and Z's, and even color them for you for your convenience. And we start by kind of creating polynomials of this form. So all of the coefficients here, the C's and the D's, are going to be randomly sampled from the finite field. And you quickly notice the kind of, we're lacking kind of one combination. So the X times X terms are not going to show up here. Everything else is randomly sampled. So what we can see here is that if we kind of fix a value to these set variables, then of course Fi is simply going to be linear in X, or affine in X. So you're kind of left with a linear system of M equations in M variables. So what this means is that actually for any given tuple, this system is very, very easy to solve, because you simply take some constants to the set variables, and then you solve, or you check if it has a solution by linear algebra. If there's no solution, just pick a different sets and kind of try again. So after a very short while, you're going to find a solution here. So I mean, this is good. Of course, the problem is this, you know, just giving out F would be very, very easy to find for an attacker. So you have to kind of mix the X's and the Z's here. And the solution to doing this would be that Alice is going to pick a secret key. So that's going to be an invertible linear mapping that mixes these variables. You can think of this as an n by n invertible matrix. So the public key she is going to publish is simply taking all of these f's that we had on the previous slide and kind of applying m in order to kind of mix the variables. So signing is still easy because Alice can indeed kind of solve for giving you y, she can kind of solve for f, as we saw in the previous slide, and then kind of get the signature s for p here by kind of applying m inverted on this. And kind of surprisingly, perhaps this does seem to work. I mean, to the best of our knowledge, this does seem to hide the x and the z's pretty well. I mean, obviously going to rename them, but kind of this seemed to do the job very well. So this is kind of how well, of course, is the problem we're looking at in analysis. So kind of this is what we're going to see in the next and sort of final section. So up to this point, we sort of talked about signature algorithms, kind of what they are, and kind of I hope you kind of have some working intuition about the U of E signature scheme. So this is, of course, where the sort of fun part begins, because now you kind of really have to dig down and kind of see how can you actually kind of try and break this particular signature scheme. So just the first type of attacks would be kind of the signature forgery attacks. So remember the kind of what you're doing is just finding an x that sort of fits for a given y. So you're solving this system of polynomial equations. And of course, this doesn't necessarily allow you to learn anything about P, but kind of it does allow you to forge a single signature. So we mentioned that this problem is NP complete, but kind of the real question is, how hard is this going to be for concrete parameters, and also kind of on average and kind of other easy cases and all that kind of stuff. Because sort of remember, all of these submissions to this signature standardization, of course, have fixed parameters. And typically there's also like a fixed, there's a fixed security setting. So and in this competition, it's a little bit awkward because it's kind of set to the difficulty of solving AES or standardized hash functions. But it's roughly, if I recall correctly, it's roughly 2 to the power of 130 something, maybe 140 something bit operations. So basically, if you have an algorithm that's below this, then you have like a valid attack, a valid break of the algorithm. If it's above, then yes, it's not going to work. So this is kind of the game we're playing. So just, I mean, how do you solve a polynomial system, a system of polynomial equations? I mean, obviously you could brute force, but there's no fun in that. So a slightly less trivial method would be something like this. So let's consider a very easy toy example. We have 4 polynomials, 4 quadratic polynomials in only 3 variables. So there's more polynomials than variables here. So I'm cheating a little bit, but hopefully you'll get the idea. I've only bothered to write F1 here, but you can assume that the rest are written similarly. And the idea is, well, as the name suggests with linearization, we're really good at solving linear systems. So kind of we want to try and force this sort of nonlinear system into this framework. So we try and kind of make a matrix out of this problem. So basically all of the columns would be all the possible monomials that we can have. And I've started filling out how this matrix is going to look for kind of F1 row. So with a color coding, you can kind of, it's very easy to see how you fill this out. And of course, you fill out the F2, F3, and F4 similarly. So as you can see, kind of, there's way too many columns here. So just trying to do Gaussian elimination on this isn't really going to give you anything useful. But what if we go up to degree 3, right? So kind of we can kind of multiply all of these F's with X and Y and Z, and that's still going to give us an equation that we want to find a 0 for. So kind of it's still in the ideal. So how is that going to look like? So now kind of done the same thing. So the rows are now x times x, y, z times the f's. The columns are actually, I'm just giving the homogeneous degree 3 monomials here. So kind of they're, yeah, I didn't bother to write out all the quadratic and lower parts. So this is kind of how x times f1 is going to look like. It had a couple of quadratic parts as well, but we didn't get that. So kind of what we can see here is the kind of the columns here are now, first of all, it looks very much more square. So that's a good start. And the columns are only 10, I think. And the rows are now 12. So, I mean, obviously, we didn't include the quadratic terms, but kind of if you do Gaussian reduction on this, then you expect like the last two to be actually quadratic polynomials. So that's pretty good, because now you can take these new quadratic polynomials, multiply them again with variables, put them again into this matrix, and kind of continue your Gaussian reduction. And actually, if you continue this process, you'd actually been able to solve the system, depending on the system, but usually you'll be able to solve the system. So it's actually a fairly good strategy. You're kind of going up degrees, making larger and larger matrices, and eventually you can kind of typically solve them by linear algebra. So let's kind of get back to, I mean, actual algorithms for polynomial system solving. And there's no easy answer because there's so many different algorithms and all of them are good in certain setting. It really depends on the number of polynomials you have, number of variables, the size of the finite field. I mean, if this is very small, you probably want to guess a lot and then do some solving. And the structure of, you know, the polynomial system itself, what's the degree, everything, all of these things play, and this, yeah, plays a role here. So it really depends on these inputs. With some examples, we talked about linearization. We had in a couple of previous slides. It's kind of a stupid method, but it sometimes works. So kind of if it's stupid and it works, it's not stupid, right? So, and actually, there are certain cases where actually linearization are amongst the best algorithms, because if you can kind of make a direct, if you expect you're in a setting where you can make like a direct big matrix that's going to be very, very sparse, and you can apply some sparse linear algebra solver here. So we're kind of using Wiedemann algorithms typically used in cryptography, then this can actually be pretty efficient. More generally, you have Grosvenor basis algorithms. So you're essentially computing a Grosvenor basis to the polynomial ideal. And from that, you can, there are ways to recover a solution. So Grosvenor bases are kind of very nice bases. I'm not going to go into too much details, but it's a well-known technique from commutative algebra. So I'm assuming it's known to some of you at least. And in fact, actually, some of the best Grosvenor basis algorithms, like the F4, actually uses linear algebra techniques, kind of similar matrices to the ones we saw, to do a lot of reductions in the ideal. So it's all kind of connected, and it's all kind of, there's a lot of linear algebra involved in certain ways here. You have hybrid algorithms. This could be, you know, guessing something and then do linearization of Grosvenor basis, for example. There's also kind of other cool stuff. So the Juevitz algorithm I have here is actually very much related, or a little bit related, I'd say, to the U of E thing. So you're kind of searching, you're first searching through the ideal for kind of certain polynomials. That's kind of it's a bit similar to kind of this form here, in the sense that if you're fixing some variables, you can kind of solve the rest by linear algebra. So, I mean, you're not going to recover these exact polynomials, but it can be it's a very interesting idea, and it can be very efficient in especially for smaller fields. And there's all these techniques for kind of, we have underdetermined system that just more variables than equations. They're kind of techniques for kind of taking that, transforming it into different systems where you have a little bit more equations than variables. And this can kind of be used in conjunction with all of these other solvers. So there's a lot of algorithms here, a lot of things. Finding complexities for a lot of these algorithms can be very difficult in general. but I'd say for the UOV polynomial systems, they're kind of well behaved. So I mean, it can be difficult, but I think we have a fairly good understanding of for the particular case of UOV, actually. So yes. The other type of attack I want to mention, and I'll go a little bit quickly here. This will kind of be key recovery attacks. So this is more about kind of trying to find the secret structure of the trapdoor. That's the or the public key, P. And of course, if you recover this, you essentially recover the secret key. So I mean, you're just as good to forge signatures as Alice. So kind of this is even worse than kind of finding or forge a single signature here. So the key observation one typically use to kind of how is P, the public key, different from a random polynomial system? Well, if you kind of recall from our description, we know that there will be a large linear space in FPN where a lot of zeros to P is going to lay. So for random polynomial systems, we're expecting, of course, I mean, they can also have a lot of zeros, but we don't expect this kind of linearity, or kind of it's not going to be a big linear space. And the reason this is linear is, of course, the kind of, well, quickly go back to UOV again. I mean, all vectors that are kind of zero along the sets are going to give you a zero, right? So kind of can be anything in the X's with zero along the sets. And this vector space is then, this O space is then this transformed by the secret matrix. So we kind of know this space exists. If you find it, you're actually breaking the scheme. But finding it can be a problem. There's a really cool attack by Kipnis and Shamir, which found that for some parameter ranges, this O will actually be a common invariant subspace for matrices you can find directly from the public key. And they came up with a very efficient algorithm. I think it's polynomial time algorithm to actually find this. And this is incidentally why we call it unbalanced, because if you kind of keep increasing n, then this attack will not work. So essentially, there used to be a balanced one. Kipnis Shamir broke this. So that's the idea there. Kind of other more recent attacks try to kind of find O, but then by kind of polynomial system solving techniques, kind of like we saw there. So essentially, for example, there's a couple of attacks here, but the latest one by Berlins from a few years ago sets a particular kind of polynomial system up, trying to find O and kind of doing polynomial system solving. So this is also an option. So I wanted to very quickly talk about quantum algorithms, since this is kind of a quantum group after all. There's not too much to say. People have looked into this in this direction, but I don't think there's like a very credible quantum attack on this construction. So people have been looking into kind of direct Grover, so kind of you're doing brute force on the polynomials, how hard or kind of how many operations exactly are going to require here. This is of course not as good because we have, I mean, brute force is not the best classical algorithm. You could also try to do kind of, try to sort of Groverize, so kind of you do a little bit of brute force and a little bit of kind of solving matrices that we saw, like the linearization techniques. This is of course possible, but also, I mean, your kind of Grover oracle is going to be like solving a huge matrix. So it would require a lot of memory to kind of, if you're maximizing for time. So this seems kind of highly unlikely that this will be realistic attacks. People are also looked into kind of AGL algorithm to try and speed up some linear algebra, but again, it kind of seems unlikely to kind of really have an effect there. So yeah. And this is really what I want to say. Just like few concluding remarks is that, I mean, I've only kind of presented some basic ideas. So there's of course a lot of details here, especially like I mentioned, there are 7 signature proposals based on UOV. So you've kind of gotten the core idea, but I mean, I don't want to dumb things too much down because there are a lot of interesting extra ideas and sort of variations to these different signature proposals. So there's that. Like I said, this is just like I wrote here, this is just the tip of the signature iceberg. So there is a lot of other cool signature schemes. I also wanted to mention that we've seen a lot of progress since 2017 in how to actually design signature schemes. So there's like a lot of generic techniques with kind of like zero knowledge techniques and MPC techniques. So you can take a lot of interesting, cool mathematical problems and like fit them into a signature now. So even if you're kind of aware of signatures like pre-2017, there's a lot of new cool stuff in this area. So, you know, if you're bored, go check it out. That's my tip there. So yeah, that's all I wanted to say.
Okay, thank you very much. This was very interesting. The floor is open for questions.
So I can start with a question.
Yes.
Hello, good morning. Do you think there's any hope of you mentioned that there are no good quantum attacks known. Do you think there could be any quantum generalizations of stuff like the Grobner basis attacks and stuff like this? Since it involves a lot of matrices, so you sort of see.
Yeah, I mean, I think, I mean, of course, it's yeah, it would just be speculation, of course. I think so I think kind of for Grosvenor basis algorithms in general, I think that would be very, very hard. There could be some speed ups to kind of linear algebra subroutines. And of course, these are really the workhorse of this algorithm. So like theoretically, maybe. and kind of this is kind of one example, because I mentioned this HHL algorithm, which is kind of really trying to speed up linear algebra. So like people have been sort of trying to look a little bit into this, but it's kind of unlikely to work in our setting. Maybe for very special polynomial systems, but yes, I mean, it seems unlikely. So.
And do you mean even a Grover speedup, or do you mean like beyond Grover is unlikely?
I kind of both from where I'm sitting. Because I mean, maybe someone here will know better about the HHL, but I think that's that. I mean, it's certainly different from Grover. So, like if it could have been applied, and maybe, and also just I mean, now I'm kind of strictly talking in the and now I'm strictly talking in like the cryptography settings. So we are doing finite fields and all that kind of stuff. So HHL kind of for linear algebra kind of work over the complex field. So kind of if you have something that's naturally there, so I mean, of course, you could have Grosvenor basis over any field, right, including complex fields. So kind of maybe there's kind of more hope for those those kind of settings. But I think like at least speaking from kind of the cryptography setting, I think it's very unlikely. But I mean, we never know, right? If something new shows up, at least from this. And yes, I mean, you also mentioned Grover, so kind of this is also like there is a certain kind of how practical is Grover, I guess, kind of. I mean, on paper, or kind of this kind of complexity theoretic, then kind of yes, but yeah, I guess like how realistic is it going to be in practice? That's also.
And I guess the same goes for HHL too.
Yeah, is that also kind of hard to do in practice, or kind of a bit unrealistic in practice, or kind of how would you view that? Or
so, excuse me, but what is HHL?
So it's, I don't remember the names of the authors. It's
Harrell, Hasidim, and Lloyd.
Okay, yes, there we go. So there is an algorithm for finding, like solving matrices over the complex number under some condition on the matrix, if I recall. So what kind of people, I guess, like in the crypto setting has been doing is kind of try to, well, first of all, our matrices will be over finite fields. But I mean, you could kind of transform the polynomial system to solve over like the complex field, but then I mean it's kind of a bit of a hack. I mean, it's of course it's not like a I mean F2 is not like a subfield of the complex field, right? So kind of you have to kind of adapt things, and I think there's certainly something getting lost in that process. So kind of, I mean, even if HHL is going to work over the complex field, I mean, there's still kind of another hoop to jump through for the crypto setting, really. So
one comment on this. So HHL gives you exponential speedup when you want to solve systems with linear equations. But
okay,
I think there's a paper by Scott Aronson, if I remember correctly, who is in the title is "Read the Fine Print." So there's a lot of buts in there, and one of them is that you will lose any speed up if you have to provide the matrix or the right-hand side in linear time. So you have to somehow provide it in maybe, in superposition efficiently, and also you will not get out the full vector, because if you have to get out the full vector, you will lose all the speed up. So there are certain hard limitations on this. So I would probably also say that it's unlikely that it can be used to speed this up.
Okay, yes, because I've been mostly reading, I think maybe they quoted this Scott Aronson article, kind of someone more coming from cryptography, but also kind of looking into this, kind of taking it seriously, seeing kind of how far it can go, and kind of, they really pointed out that there's a lot of these things that has to kind of go wrong or go right, I suppose. Yeah.
Right. I just Googled and I found out that HHL is at the center of this quantum machine learning movement. So then it makes sense.
Yeah. So it's a kind of also at least there, the conclusion of the article I was thinking about is kind of, like highly unlikely. Maybe there's some room in certain very specialized polynomial systems, but it's not. Yeah. It seems unlikely is kind of the conclusion there. So.
Okay, thank you very much. Maybe we should round it off for today. Thanks again for the very nice presentation.